is Lucas, okay, and now we're going to talk about Node.js under the hood. So, well, first, a little bit about me. My name is Lucas. I'm a lead engineering architect at Nindo. It's an AI company, and I'm also a Microsoft MVP and Google Developer Expert on web technologies and developer technologies. The slides for this talk they are already on my Twitter, okay, so it's this link over there. You can follow along if you want. All the other social networks and all the other social contacts are on my site, lsantos.dev, okay? And I have one other disclaimer to do, because there is not even close to enough time for me to talk about everything in Node.js in 40 minutes. So basically, I compiled a guide, okay? It's in my GitHub. It will become like a lot of articles. And I very much encourage you to read this guide because it's very complete, it's very long, okay? So let's get started, okay? So what is JavaScript, okay? Basically, JavaScript is defined as a prototype-based language. Let me just... Yeah, now it's good. Okay, so it's defined as a prototype-based language, which means that we don't have inheritance by classes, we have inheritance by prototyping. So basically classes are not existent in JavaScript. It's also a dynamically typed language, which means that the compiler or the interpreter will infer the types during the execution. Okay, it's also an interpreted language, which means that we don't have ahead of time compiling. The code is executed, it's compiling, it's parsed, transformed into a series of subroutines, and then transformed again into machine code. Okay, so basically we run the code as we compile. Okay. It was created in 1995 by Brendan Eich while working at Netscape as the main language for scripting in that time, and conforms with the ECMA 262 standard. ECMA stands for European Computer Manufacturers Association, I believe, and it's the full standard for scripting languages. If you will remember, like ActionScript, if you program Flash, I guess, ActionScript is one of the other languages that are also compiled with ECMA 262, okay? And it's maintained or defined by TC39, so ECMA is the specification, and the TC is the technical committee number 39, who actually maintains and evolves the language, okay? So now we're going to talk about Node.js. Node.js is a JavaScript server-side runtime, okay? It's not a framework, it's not a language, it's JavaScript runtime. It's not the first one to actually execute code on the backend, okay? Because Netscape had one in 1999. It's called Netscape Server, so it's not the first one. It was created by Ryan Dahl in 2009, presented at JSConf EU, and it was later sponsored by Joint, okay? So basically, it has an event loop which grants the Node.js a unique ability of non-blocking I/O signatures. So which means that Node.js will never stall. You'll never have freeze on Node.js because Node.js does not block I/Os, okay? And it uses V8 on the backend to compile JavaScript. We're going to understand this. So I have seen an image, a lot of images in the internet, and there's one that actually describes Node.js perfectly. This is the image, okay? Basically, Node.js took what was the slowest language of all times back in 2009 and coupled it with one of the greatest technologies, one of the best pieces of software ever written, which is V8. Because now Node.js runs almost as close as C or C++. JavaScript can run at the same speed as C or C++ if you run Node.js in certain codes, of course, not all the codes. In Ryan Dahl's words, Node.js is actually a set of libraries, C++ libraries on top of V8 that provides JS functionality to work on the backend, okay? It looks like this, okay? Node.js looks like this. You have your code, you have V8, you have some core modules, you have some C++ bindings, libuv, and some dependencies. Node.js depends on C-Aries, HTTP, OpenSSL. It's some of the C dependencies that Node.js depends on. And then you have the operating system, which converts this to machine code. So in order to better explain this to you, the best way to explain is by doing. So I'm going to take a function. Okay, this function is going to accompany us through this presentation. It's a simple function that reads a path and reads a file and prints on the screen. Okay, I have converted the function to promise here, so this is something we will do later. Okay, but why did I choose this function? Because fs, the file system is what differs Node from the JavaScript in browsers, because we actually have access to file system within the backend. So FS is not a Node provider, is not a V8 provided package, is not a JavaScript package. VFS is a C++ binding. Okay, so this is the source code for read file, the function read file. So you're going to say, well, this is JavaScript, right? This is JavaScript. All the interfaces we call in Node are written in JavaScript and call C++ bindings on these two lines. Okay, all the links for the sources are on the code. Okay, so you have this internal bindings fs, which loads a file called nodefile.cc, which is a C++ file that loads this fs namespace, and from this fs namespace it reads the fs rec callback. The rec callback is the async callback we pass to read file function when we want to get the result. And this is how it looks like in C++. So this is fs rec callback. This is our callback function in JavaScript we pass to Node when we want to get this thing async. Okay? So basically, how JavaScript works. How can we bind these two things together? So C++ is one different world, JavaScript is another different world, okay? Most part of our code is JS, okay? So basically, I'm going to talk about the high level parts first, so JS, and then we're going to go down and down until V8, okay? So the JS is composed of two main components. The first one is the engine, okay? The engine is basically responsible for running all the JS code we write. JavaScript is basically text, okay? So when we run it, it needs to be parsed, interpreted, and then run it. So basically, the engine is the one who does all the heavy lifting. Okay, so it is responsible for running all the JavaScript code we write, and also responsible for parsing and interpreting the JavaScript code, memory allocations, the call stacks, garbage collection, code optimizations, and some other things. Okay, there's not one only engine. Okay, V8 is not the first engine, it's not the only. There's a lot of other engines. Chakra from Microsoft Edge. There's SpiderMonkey, which was created by Netscape and now is used on Firefox, Nitro, and so on and so on. Okay, since this is a basic diagram of how a JavaScript engine works. So we have a heap, memory heap, where the allocations actually happen, where our variables is being declared and so on. And we have the call stack, okay? Basically, you have heard this phrase once, okay? This sentence, sure. You have heard that JavaScript is single-threaded, okay? But what the hell does it mean to be single-threaded? Single-threaded means we have only one call stack. Therefore, we can only execute one thing at a time. Okay, this is why this is very limiting, but this is actually very rewarding because it's very easy to implement on JavaScript. C++ is not single-threaded. Keep that in mind. Okay, but what is a call stack? Okay, so the call stack basically is not a part of JS. It's not even a part of V8. Okay. It's a part of V8. Sorry, the stacks are structures that serves as a collection of elements. Okay, so imagine this: you have a series of boxes and you want to stack them up upon each other. Okay, so now if you want to take one of the boxes on the bottom, you have to take all the boxes on the top. But if you want to take one box on the top, you can easily take them. So this is how stacks work. You put things on top of the stack. You take things off top of the stack. Okay, this is called LIFO, last in, first out. Okay, keep that in mind because stacks and queues are different only by this. Okay, it keeps track of all functions we have. So basically, this is the program counter. We have. So basically, every function call puts a stack frame on top of the stack. Every return statement takes a stack frame on top of the stack. And basically, this is how the stack works. Okay, and what is a stack frame? The stack frame is a function call. Okay, every function we call is a stack frame. It's put on top of the stack, and so on. Okay, so let's exemplify this. Take this function. Okay, it's a simple multiply function. We're calling print square. Print square calls another function called multiply, and then prints it on the console. Okay. Well, in the first step, everything is empty. Okay, the call stack is empty, everything's empty. Then we start executing. Our language is interpreted. So the interpreter will find the first function call. The first function call is print square. Okay, okay, here. It puts on top of the call stack, okay, so now we go into print square. Then it calls multiply, it puts on top of the call stack again. It goes to multiply, multiply only returns, so it takes off the top of the stack, and then calls console.log, which prints on screen. Then it returns, and then it returns. The last step of every program, FJS program, is equal to the first. When the call stack is empty, there's nothing else to execute, okay? The second part of JavaScript is the hosting environment. Okay, the engines is only responsible for running one tiny bit of JavaScript. So it runs our code, but where the JavaScript code is running, wherever the code is running. So since JavaScript is almost everywhere, it can be like a browser, can be a server, can be a toaster, can be a plane. This place is where the hosting environment is. So basically, it provides external APIs so JavaScript can communicate with those external services like the C++ bindings we talked about. It actually handles async queues. So most environments are not single-threaded like JS. Okay, so we have to have something to handle the scheduling of async tasks. This is the real diagram of how the JavaScript environment works. So we have these web APIs here, and the event loop and the callback queues. These web APIs are actually what makes JavaScript so great. Okay, this can also be called external APIs. In Node, these external APIs are our C++ bindings I just told you about. They provide functions like set timeout, fs, read files, the net package from TCP and UDP sockets, and so on. Which sends our code to a different thread, because C++ is not single-threaded. So it sends our code to a different thread. When this code is finished, these external APIs put our callbacks into the callback queue. And the event loop takes care of taking those callbacks off the callback queue and up into the stack. Okay? But how does functions provide the result to the main thread again? Okay? This is where the event loop comes in. The event loop handles all scheduling for async functions inside JavaScript. Okay, the event loop, it's basically built around callbacks. Node.js was very much known in the beginning by callbacks, so everything was a callback. Remember callback hell and now promise hell, and there's a lot of things. So basically Node is async. Node is based on callbacks. Callbacks are functions that should be executed at a later time because we only have one main thread. So only one code runs in the main thread while all the other codes are separated in a later thread. Okay, but how this thing works? How does the callbacks work? Basically the event loop, it's not provided by the JavaScript or V8, okay? It handles async code execution. So it puts the callbacks into the callback queues, and in Node, it's provided by libuv. Okay, libuv, which we're going to talk about later, is another dependency. It's a C dependence on Node, okay? It's not a part of V8, and it's also not a part of JS, okay? It's provided by Node itself, okay? So libuv is a open source library to abstract several key parts of the OS, like read files and so on. It was initially created by Node, and created to work with Node as an abstraction around libuv. Okay, it provides not only the event loop, but also TCP and UDP connection and sockets, async DNS resolutions, FS events like read file, interprocess communication, child execution, shell control, and so on. Basically, the interface to the OS. Okay, thread pools, clocking like set timeout, and so on. And this is all put onto the callback queue. Okay, callback queue is where all the callbacks are scheduled to be executed, basically. So it's a queue which resides along the event loop, and the event loop checks for everything in this queue to put on the call stack again, okay? The difference between queues and the stacks is that stacks work on the LIFO ordering. So we take the first and we put the first. Queues are actually the other way around. We take the first, but we put on the end of the queue, okay? So this is the only difference. It's called FIFO. It's first in, first out, okay? This is the callback queue here. So let's take our function, our read file function. Let's simplify it a little bit, okay? This is our callback. So this is the callback for read file function. This is what's going to be passed to do fs hack wrap function. And let's simplify this to remove the promises. Let's only work with the callbacks. So now we have our call stack. we have our external APIs, we have our callback queues, and everything is bound together by the event loop, okay? So basically, we're going to execute a starting. So this is going to print starting at the console. Then it's going to be returned. Then fs read file is going to be called. Since fs read file is a C++ binding, it's going to call the external API for file, and it's going to put a file callback into the queue, okay, into the external API. So it's going to be executed on a later time on a different thread. So, okay, it's done, it's returned. Now we execute the next function. So console.log is going to be printing ending, okay? Well, have you seen that this is already completed? But why didn't this thing execute it first? Okay, why it is not executing it? Well, the thing is that later doesn't actually mean later. Until AS6, there was no consensus about how the event loop should work, how the async queues should work on JavaScript. So basically, it was like a war zone. Now we have some fine-grained control, which means that event loop needs to wait until the call stack is empty in order to put another callback into the call stack again. Okay, so now the call stack is empty. We can put our callback on the call stack. This is going to be executed. So this is going to call console.log. There should be another stack frame here from toString, but okay. Then it's going to print the file contents, it's going to return, And once the call stack and the callback queues are empty, the event loop finishes the process. Okay, so this is how Node knows how, when it needs to finish the process, when it needs to exit 0, exit 1, and so on. Okay, so if there's nothing on the queues and nothing on the call stack, then the Node process is exited. Okay. Let's go on. So basically, we have the difference between prior ES6 and post ES6 after we had some consensus of how async should work is that the promises implementation, the native promises implementation actually put on the scope of the JS engine to handle async callbacks because we need some finer grained control of how we should implement our promises because we don't have any assurance of how things are going to be executed. Now we do. Well, the microtask queue, I'm just going to call job queue, okay, because microtask and macrotask is so much close together. So basically, a microtask queue or a job queue is a queue that is attached to the end of every tick of the event loop. A tick in the event loop is the name we give to each iteration of when the event loop takes a event from the callback queues from the queue, whatever queue, and puts on the call stack. This is a tick. So this job queue is attached to the end of every tick, which means that all the jobs will be executed first and the callbacks later. Okay, so promises execute first and callbacks execute later. Okay, this is assured because since we have those two queues, now we know that when we put a promise and we put a callback, the promise will be executed before any callbacks execute. Okay, this is some examples of microtasks. So these are microtasks. Process next tick is very famous in Node. So if you do this, you're going to schedule your execution to the next tick, to the next execution of the event loop, which is ASAP, which is just after. Okay, so now the macrotask queue is the callback queue we were talking about earlier. Basically, I'm going to read this specification because there is a specification of how this queue should work, okay? According to that specification, exactly one macro task should be processed from the macro task queue, the callback queue, in one tick of the event loop, okay? After that macro task is processed, okay, after that macro task is finished, all the other available micro tasks, the jobs, should be processed within the same tick, okay? So all the promises, all the observables, everything should be processed within the same tick of the event loop. But there is something, if you think straight, a promise can add another promise, which can add another promise, which can add another promise, then this would call starvation because promises would never stop executing, callbacks would never execute. So in order to guard this from happening, Node created a variable which is called process max tick depth, okay? It's default to 1,000. So after 1,000 jobs, Node will stop the event loop, execute a callback, and then return to execute another 1,000 jobs, okay? These are examples of microtasks or callbacks. So set timeout, set interval, set immediate, and any I/O operation like read file and everything else that goes to in and out is a macro task. Okay. Basically, what would happen if we executed this? So let's look at the code, okay? We have a console.log, which is a synchronous function, okay? We have some set timeouts, which are macro tasks, which are callbacks. We have a promise that resolves to a macro task. So we have a micro task, a job, that resolves to a callback, okay? We have another set timeout. We have a promise that only resolves to the execution of the function, which is a simple job, okay? So let's take this. We're going to execute, okay? Print start, return. We execute set timeouts put on the queue over there, return, another set timeout, put on the queue, return, okay? So now, the first callback is executed, okay? It's finished. But the call stack is not empty, so it's not going to execute, okay? So now we are going to execute the handle for the promise, but promises are jobs, okay? So the handle is put on the job queue, not on the callback queue, okay? Remember, this thing executes first. Okay, so now the set timeout is going to be called, is going to put another callback there, then it's going to return. We're going to execute the next handle for the next promise, which is going to be here, okay, and is going to return. Okay, now the call stack is empty. What would happen on our call stack? Well, the first job is going to be executed. So the handle is going to be here. So this is the end of the tick. So it's going to execute in the same tick. So it's going to execute the handle, it's called set callback, it's going to put another callback in the queue. Okay, then it's going to return again. Is there anything else in the job queue? Yes, so it's going to execute the next job. So the function is going to print console.log promise, okay? Then it's going to return and return. The call stack is empty, the job queue is empty. So now we can execute a callback. Now it's going to put a callback here, execute console.log. Okay, now the call stack is still empty. We can execute another job, another callback. The same thing happens, another console.log, another timeout, returns, and so on, okay? Then the same thing with the third. And lastly, the same thing with the last callback, okay? So it's going to execute console.log, promise timeout. This will be our final result, okay? If you want to test this, once you can copy the code, it's on the guide too, okay? It's pretty nice. Basically, it's going to finish. Now, neither the call stack or the job queue or the callback queues are full or filled or something. Then the event loop says, okay, now there's nothing to do. Let's finish the process. The program ends. Okay. Now let's talk about V8. Right now we were talking about only, this is V8, okay, call stacks are V8, but we're talking about the integration from V8 and the libuv on the event loop. This is the binding their two together. Now we're going to talk about V8 itself, okay, especially about their compiling pipelines. So basically, V8 is a Google engine that was designed for Chrome. Okay, later in 2009 or 2010, I believe. I don't know. I don't remember the exact date. It's open source and made to have a high performance. Okay, so it was made to be fast, and it is fast, really, really fast. It compiles not only JavaScript but WebAssembly as well. It's written in C++, and it implements the full ES syntax. Why am I saying this? Because you're going to see that it was not always like this. Okay. It can be standalone. You don't need to run V8 and Chrome. You can run like V8 whatever you want. Okay, you can compile JavaScript whatever you want. Spruino is a small board that runs V8 and compiles JavaScript. Okay, no, it's not V8 actually. It's another engine, but it's based on. So it's pretty nice. You can do with JavaScript and the engines like this. So everything starts with an abstract syntax tree. Have you ever heard about an abstract syntax tree? Who ever heard about an abstract syntax tree here? Okay, so I have heard a lot. Abstract syntax trees are a tree representation of the syntax of a code, okay? Not what it does, but the syntax itself. So I took the liberty of taking the first line of our small function. This line would return this abstract syntax tree, okay? So basically, this line goes to this. See that the syntax tree is only about syntax. So we have the requireable variable declarations, identifiers, call expressions, in here, the kind, const, it's this, const, okay? So if you read, it's actually pretty straightforward. You can actually read and mount the code in your head, how these things work, okay? And how, there's another thing that V8 does, okay, keep that in mind, the AST, keep that in mind. How does V8 do to make a synchronous, a multi-threaded language, like a statically typed language like C++, to execute JavaScript, which is a dynamically typed language, okay? How does V8 do this? This is how hidden classes comes in, okay? So now, remember, let's imagine you have this code. Okay, JavaScript being dynamical means that you can actually create code, create properties on the fly. Okay, so basically we have a simple object. This is common. Okay, everyone have already done something like this once. This is common. So we have a simple object, an empty object. We create an X property in an object. Now the object has X. Okay, and the value of 1. Now we create the Y property, and the object has now another property called Y. Okay, this is dynamically typed languages. V8. Under the hood, it actually creates a hidden class. This hidden class is going to be a pointer to your variable. So first, we created an object here. Remember? This empty object will be the hidden class C0. Next, we added the X property. Now, V8 creates another hidden class, points it out to the first one based on the C0. So C0 is the base for C1, and adds another transition from C0 to C1. So now, C1 is an object with an X, okay? An X variable and an offset, okay? The offset in memory is how many bytes the compiler should jump to get to the value, okay? So this is easily obtained by the typing variable and so on. That's pretty nice. There's more about this in the guide. But we added a new property, Y, right? Remember? So now V8 creates another class, C2, and does the same thing. So if you want X, you take offset 0. If you want Y, you take offset 1. This is why people say that that actually property order matters. As a performance tip for you, V8 optimizes the code as it runs. Okay, so it also de-optimizes the code. I'm going to explain this about this later. So if you switch the order, if you create Y first and then X, the whole hidden class for Y or X will not work, because C1 is the hidden class for X on the offset 0, not offset 1. So V8 will create another set of classes just for this exchange of properties, which means that your code will run more slowly than it would if you just kept the same properties forever, okay? So the less you change the order or the properties, the types of your variables, the better it is for your code, the faster it's going to run, okay? V8 is based on pipelines, okay? V8 is composed of 2 components, and you had an old pipeline and a new pipeline. I was going to explain this first. AOT and JIT, okay? AOT means ahead of time compilation, which means that you have to compile the language first, generate an executable, and then execute this executable, like C, C++, or Go, for instance. We have JIT compilation, which is just-in-time compilation, where the code is actually the input, and the interpreter runs the code as it is reading the code. So this means that we can optimize the code while we are running the code and getting type feedback on how this code actually works, okay? So basically, the difference between one and the other is the compilation time, okay? The old compiling pipeline on V8 was abandoned in 2017, but it's important to talk about it because it was composed of 2 components as well. The first component is Full-Codegen compiler. It was a blazing fast compiler that compiled all, actually a parser that parsed all JavaScript code into machine code that the optimizing compiler could actually read, but the important thing on JavaScript on browsers is that you run JS code fast and quickly, because you don't want to be sitting there waiting for your page to execute, okay? So Full-Codegen did this. It has a very, very, very blazing fast compiler that created JavaScript code and executed as fast as it can be, but the code was not optimized, okay? So basically, it was relatively slow. Okay, it handles also the type feedback that we need. So if you execute a lot of functions with an integer, for instance, it is going to say, oh, this function executes with integers. And then the next compiler, the Crankshaft compiler, would be able to optimize this function for integers, okay? So Crankshaft is the old optimizing compiler for V8. It was using during a time with V8 and with the new compiler and the last one. Basically, the objective of an optimizing compiler is to implement optimizations in runtime. Okay, there's a lot of optimizations. It's all in the guide as well. Basically, it takes the type feedback from Full-Codegen and then it generates a new code, an optimized code based on this type feedback, and uses on-stack replacement to replace your running code, or non-optimized running code, with optimized code. So imagine the stack, you replace the first stack frame, and then with an optimized code on the next step frame on top, okay? But if Crankshaft cannot actually execute, so imagine you have a function where you actually sums two numbers. Okay, so the first number is an integer, the second number is an integer. You run this function 100 times. So Full-Codegen knows that this function is calling on integers. Okay, so now Crankshaft optimizes this function for integers. But now you pass it on a float number. Now Crankshaft doesn't know what to do. So it deoptimizes the function, it takes off the optimized function from the call stack on runtime, it deoptimizes it, and it can run, well, this is actually the first problem that Crankshaft had. It can run up to 100 times slower. This is called the optimization cliff, okay? So the new compiler pipeline, it's composed of two components as well, okay? It's this one. So there is an interpreter called Ignition, and there is a compiler called Turbofan. Ignition is now the new Full-Codegen compiler. It compiles code in bytecode really, really fast and executes it. And then we have Turbofan compiler, which is an optimizing compiler that replaced Crankshaft. Okay. The Turbofan is was created actually to handle AS6 syntax because Crankshaft did not implement the full ECMAScript syntax. Okay, so we could not handle actually AS6 for optimizations. Then it was designed first to be a WebAssembly compiler, and then use the Sea of Nodes approach, which I'm not going to talk about, but this the representation of the code as a graph of nodes. Okay, receives the bytecode directly instead of the AST or the machine code, which means that you can actually optimize the bytecode prior to execution. Then it means a smaller bytecode, a smaller memory footprint, and executes really, really faster. Okay. It's divided in layers, okay? So we have the front end, which is responsible for generating the bytecode, the optimizing layer, which optimizes, of course, and the back end, which generates the machine code the computer can run, okay? It's also fixes that the optimization cliff because now, since the Turbofan can handle all the cases, it does not de-optimizes up to 100 times slower than it was before, okay? So this was the mixed pipeline that V8 had for a time. So before the new compiler pipeline was put into place, everything was used. So we had Full-Codegen, we had Crankshaft, we had Turbofan, we had Ignition as well, and then we had the AST. Pay attention to this part. ASTs is the source of truth here. Everything goes back to the AST, okay? So basically, all the compilers needed to know the AST prior to compilation so they could actually gather information about this. With Turbofan, with Ignition, this was not necessary anymore. So this is the new pipeline, okay? So this is the current pipeline. The AST only generates bytecodes, and these bytecodes are passed to Turbofan. So now Ignition is one of the most interesting parts of V8 because it was firstly created to be an interpreter, generating optimized bytecode to reduce memories on low-end devices like cell phones without less than 500 megabytes of RAM, basically. It does this by generating smaller baseline bytecodes, which can be very, very fast and can reduce the time that the compiler takes to read them and reduce the memory footprint on the browsers, okay? It was focused on low memory devices. It's not a parser, okay? It's an interpreter because it receives bytecodes and outputs bytecodes. The AST is not a source of truth anymore, as you may see on the last slide. The AST is now only used to generate the bytecodes in order to Turbofan to read, okay? Or Ignition to read, okay? And the most interesting part is that Ignition uses Turbofan's backend to generate machine code that Ignition can optimize using Turbofan's optimization or low-level optimization. So the bytecode that goes out of Turbofan or goes out of Ignition at first is way more optimized than the bytecode that was generated by Full-Codegen first. Okay. So the ignition pipeline is pretty straightforward. Okay, so we have a parser that parses an abstract syntax tree. This is not going to fade away. Okay, the abstract syntax tree is very useful. It needs to be there because it's a interpreted language. Then the syntax tree goes to a bytecode generator, which is Turbofan's backend, generates a bytecode. This is the optimization it does. So join me in this. It optimizes the registers, optimizes the people optimizations. I'm not going to explain this one, but bad code elimination. If you optimize a code, if you actually compile a code and go it on to a lot of that code, this is a much bigger code than if you took that code off, right? So that code is actually increasing the time, the memory footprint from the code. So with a smaller code to read, Turbofan can actually run very, very, very fast. Okay. So what are bytecodes? Bytecodes are a intermediate representation from machine code and human readable code. So it's in the middle. Okay. So technically, bytecode is machine agnostic. It can be compiled to any language or any architecture. Okay. Ignition is a register-based byte interpreter with an accumulator. If you remember the classes you took from, like, I don't know, computer architecture, CPUs are based on registers. Okay, so this is almost exactly the same thing. This is bytecode. Okay, this is bytecode. This is the code. This is the bytecode, and this is the machine code that the processor reads. Okay, this is JavaScript. This is assembly. Okay. You can get this bytecode running this command. So if you go print bytecode, and you can filter this bytecode like for the function you want, and the file, you get this bytecode. I'm going to pass it on very quickly of how this thing works, but go on with me. LDA SMI is load accumulator small integer. So it's basically loading a small integer, number 100, into the accumulator, that accumulator I talked about. Okay, so it's 100, this 100. Okay, now it's subtracting from the accumulator the value of A2. A2 is argument index 2. So index 0, index 1, index 2. So it's C. Okay, C minus 100. It stores that value into the accumulator. Then it's star R0. Star is you store accumulator, register into accumulator. Okay, accumulator into registry. It's the other way around. So basically, we are defining a variable. R0 is register and the index of the registry. Registers are local or global variables. So basically, we are creating variable D here, storing everything from this subtraction into variable D. Then we are loading into the accumulator another register, which is A1. A1 is B. Okay, so basically that's the function we are calling now. We are multiplying B by D, which is R0, multiplying by R0, and then in the end we add A0, which is A. So this is the function, and then we return the value from the accumulator to the function, to the call E, actually. So this is very explained on the guide. Okay, there is a whole list of bytecodes in the V8 source code. It's called bytecodes.h, from header. You can read them. There's a lot of bytecodes in there. And this is actually in JavaScript. So JavaScript goes through this every time. So let's put it all together. Okay. So let's take our code and execute them. So this code executes, go on through ignition, generates this bytecode. I'm not going to explain this. Okay, but generates this bytecode. This is only for read file sync, okay? This is only for this function. Then it goes through all this pipeline to generate machine code, and then the V8 executes this code like this. I just stepped off the first two functions because it's only assigning functions. Then it's going to call path.resolve. It's going to return. Then it's going to enter our immediately, I forgot, IIFE, which is immediately invoke the function expression. Then it's going to call read file async. Read file async is a promise, which is going to put a handle here. Okay, this handle. Then it's going to return. There's nothing else to execute. There are jobs on the job queue, like we said. The job is going to be put back on the queue, on the call stack. Then we are going to execute read file. Read file is an FS operation, which is a callback. So it's going to be here. Then it registers the callback here. the call stack is empty, the job queue is empty, the callback is executed. It calls resolve, which calls callback, which calls toString, then returns, and then we print our thing on the console. Then it returns, nothing on the job queue, nothing on the callback queue, nothing on the call stack. The event loop ends the process, the program is ended. Okay? So guys, please, if you want, okay, read this guide. I'm going to publish this on my Twitter. And when I create a lot of articles about this on my Dev2 account or Medium or both, I don't know. But I'm going to publish this whenever I do this. And well, thank you all. This is what I had to start with.